Okay, now I'm recording. I think, do you see a little dot there? I see a little dot that tells me I'm recording. Hopefully you guys see something. All right, so what we're covering today is 4.8 differentials. And this is just a way of approximating. So differentials is a way of approximating. So it says, here's a formula for tangent line approximations at a particular point. All right, and our particular point is C. So first we take the function at that point and find the answer. Then we take the derivative of that function and plug in that point. And then we use the change from x to that point. This is the change in x, and we'll look at that here in a second. So this is the formula we're going to be using for differentials, finding the tangent line approximation. So let me erase this and let's get going. So first, find the tangent line approximation for this function at this point. And the first thing we need is to find the derivative of this function. Once again, the derivative of this function, the derivative of 1 is 0. The derivative of sine x is cosine x. So our derivative is just the cosine of x. And we're going to approximate this function where x equals 0. And once again, here's our function, x equals 0. And once we say x equals 0, but at the point we're also saying c equals 0. Do you see everywhere there's an x value, we put 0 in it? We put 0 in it, and in other words, x is the c. And we still leave the x there, but we're putting, this is c, 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 and c, I put 1 there, but c equals 0. C equals this. This is the point that we're doing the function on. So first we plug 0. Now let's put it over here. First we plug 0 into the regular function. 1 plus the sine. Now we might need our unit circle. So on my unit circle, I should have bring all my calculus stuff out when I teach in calculus class. On the unit circle, look at the sine of 0. It's very blind. I'm blind here. Sine is the y, and if you look at the sine of 0, can somebody just yell out what the answer is? Sine of 0?
Pi.
The sine of 0 is 0, right? When you look at the unit circle, at 0 right here, we have 1, 0. The y function is the sine. So that's 0. So f of 0 equals 1 plus 0, which just equals 1. Do you see in here, f of 0, this changes just to 1. By the way, this is a small y. Y equals 1. F of 0 is 1. Now we're going to find f prime 0. Well, f prime is the cosine of x, cosine of 1. So we want to find the cosine of 1. We want to find a cosine of 0. We're plugging 0 in, not 1. So look at the cosine of 0. The cosine of 0, the cosine is the x value. And so this equals 1. So f prime 0 equals 1. This changes to 1. And then we have x minus 0. Do you see now we're just plugging c in here. We put the 0 into here. We put a 0 into here. We put a 0 into here. And this all comes to 1 plus 1 times x minus 0 is 1 times x. And you can rewrite this y equals 1 plus 1x or x. And that's it. This is the approximation. This is the find the tangent line approximation. This is the tangent line approximation to 1 sine x. In the book, it shows a picture of that. I'm going to erase this and try to draw you this picture. So if we have a graph, 1 plus the sine of x looks like this. I mean, just if you look just right here, just in the small little space, this is 1. This right here would be negative pi over 4. And then this right here would be pi over 4. If we just drew a quick point of this. This graph that we just, this equation we just created, y equals x plus 1 or 1 plus x, is the tangent line at when x is 0. And if you look, the tangent line through that particular point looks like that. That's the equation for that line. That's what we just approximated, the equation to that line. All right, so that's that. Let's move on. That's the first slide. So differentials kind of look like regular derivatives. They are. Here's a function, y equals x squared. Here's its derivative, right? We change y to dy dx. We're taking the derivative of y with respect to x. And the derivative of 2x, bring the 2 in front, subtract 1, is 2x. The derivative of x squared is 2x. Now, we call it a differential if, let me erase, oh no, I'm not going to erase. So I have, once again, this is dy dx equals 2x. We call it a differential if we bring this x to the other side. It's divide by x. The opposite of dividing by x is multiplying both sides by dx. Those cancel. And we're left with dy equals 2x times dx. That's the differential. Do you see the derivative of sine of y? 2 sine of y is 2 cosine of y. If I take the dx to the other side by multiplying both sides by dx, we now call it a differential. This is just the change in x, right? dx is the change in x. We're going to call that the change in x. So when we say when they say find the differential for x to the 4x to the third, find this differential, it's just the same thing as taking a derivative, 12x subtract 1 squared, and then you're going to have the dx. That's the differential. I mean, this is the derivative. We add the dx and we call it a differential. And the reason why we do that, we're going to show you in the next coming slides, I think. So there's not much difference between a derivative and a differential. we just bring that, if we're taking find the differential, we just take the derivative and bring the dx to the other side.
So in this case, that dx isn't really a number. We're just
Right.
the end of it.
I mean, when later on it's going to be a number. It will be a number.
Okay.
And let's see. Yeah, in the coming slides, we only have a few slides left. It will be a number.
Okay.
Okay. Okay, so here's the next slide. Once again, the differential of y, the dy part, is the change in y. So we show you that you can, instead of saying dy, we can say the change in y. And when we start saying the change in y with that, the dy differential, that's where we're approximating. Once again, we're back to algebra, where we're using 2 points to find a slope. The change in y is, right, the slope is the change in y divided by the change in x. Another way of saying slope is the change in y divided by the change in x, dy dx. And another way of saying slope is the first derivative, dy dx. So that's why when we said if we have y, we take the derivative, we change it to derivative of y with respect to x. So that, I mean, this is slope, the change in y over the change in x. We can also write the change in y over the change in x, dy dx. Once again, slope, change in y, dy, change in x, dx. This is the same. Well, let me show you how we get to this here. Once again, y equals the function of x, right? Y equals the function of x. If we take the derivative of both sides, we get the derivative of y, which is dy dx. The derivative of the function is f prime x. Now, if I take the x to the other side, I get this. And I can change dy to the change of y. So they're just showing you, you know, the algebra of moving things over to the other side and changing dy to the change of x, or changing dx to the change of, you know, the dy to the change of y and dx to the change of x. All right. So let's compare change of y and dy. Once again, change of y is algebra. When we talk about algebra, this is an approximation. The dy, we found the derivative, the slope at one particular point. This, and I'm going to call that the exact. If y equals x squared, find dy when x equals 1 and dx equals 0.01. Okay, so if it is, so here's a question, a problem. Find dy if we have this function, y equals x squared. Well, we can change to find dy. Dy is y prime. Another way of writing y prime is dy over dx, where we're taking it with respect to x. The derivative of this function is 2x. Derivative is 2x. And then I bring the change of x over, or the dx over, dy equals 2x dx. And that's what we have here. Once again, this was the derivative. This was our 2x. and then we had the dx. You see, dy equals f prime times dx. And when x equals 1 and dx equals 0.01. So for dx, we're going to put the 0.01 here. For x, we're putting 1. Wait. Yeah, we're putting for x, we're putting 1. Sorry. Yeah, right here. And for dx, we're putting 0.01. And when we do this math, dy equals 0.02. That's what we get right here. Okay? So the dy equals 0.02 there. Now we're going to do, that's an exact answer. That's the derivative, and we found dy equals 0.02. We're now going to do an approximation, and this is the change in y minus y, right? If you remember, slope equals y2 minus y1 divided by x2 minus x1. Once again, slope, another word for slope, I'm going to erase the m. Another way of writing slope is the first derivative, and I'm going to erase that. Another way of writing the first derivative is dy dx. So this is y2. This is y1. You see, we have y1 and y2. y2 minus y1. The change, we have a number, and then we added something to that number to make it different. So that's y2. y2 minus y1. Well, let's find out what the function equals. I'm going to erase this up here. I'm going to keep that dy there that we got the first time. Actually, I don't have to keep it. I have it over here. I have it right there. So we're now going to do the change in y, which equals fx plus change of x minus f of x. Well, we know x is 1. The change of x right here is 0.1. Remember, dx is the change of x. 0.01 minus, put 1 into the function. So 1 plus 0.01 go into the original function. The original function is x squared. We are going to put 1 plus 0.01 is 1.01, and we're going to square it, minus the function 1. Once again, the function, we're just plugging 1 into the function this time. And when we put this into our calculator, we get 0.0201. They just wanted to show you the derivative is this 0.02, but when we do differentials, when we do use differentials, the change of y, instead of using dy, when we use the change in y, we get a very close approximation to the actual derivative. This is the approximation. This is the actual answer. And Newton used this method to do square roots, which is, I think, going to be the next problem that we're going to cover. I think it was Newton that did it. I'm almost certain it was Newton that did it. Oh, I read that somewhere before. So here is how, back in back before you had the square calculator. Somebody tell me on your calculator what the square root of 16.5 is. So on my calculator, I'm going to put 16.5 and take the square root. And I get 4.062019202. It's an irrational number. It goes on forever. That's the square root of 16.5. How did they do this back in the, let me see, 1600s? It says both Leibniz and Newton are credited with creating calculus. So
I get the feeling that's what the abacus was for.
yeah. So, but all these decimal places, how could they take the square root of 16.5? Remember, we did that other thing until we got really close to that number where we did iterations over and over again. Well, this is an approximation for the square root of 16.5. We're using this same formula. So this is really important to understand it, because I see every semester students don't understand this formula. Students don't understand this formula. So the x, we're going to take the square root of 16.5. The x is a known perfect square. So the x has to be a known perfect square. So in this problem, our known perfect square is the square root of 16. It equals 4. Okay? So x in our problem equals 16. That's our known perfect square. X is 16. The extra part is the change from 16. And the change, since we're going to do 16.5, the extra part is the 0.5. The change is the 0.5. So it's really important you understand x is always going to be a perfect square. Always going to be a perfect square. And I'll show you an example where what? I can't use a perfect square. Yes, you can. So we're going to use the formula here. First, take the function x. And by the way, the function x, this is putting 16. I'm not going to put 16 in there yet. But this is just the square root, right? Our function is just the square root function. Let me take that 16 out of there. And so here's the square root function. I'm going to change it to this. They're the same thing. Anytime I take, right? By the way, I need to find the derivative of that function. So I'm going to change the square root to rational exponent so I can take the derivative. So now I'm going to take the derivative of this function. You bring the 1/2 down. And then you subtract 1. 1/2 minus 1/2 is a negative 1/2. So our derivative, you can call it, you can make it look like this, or you can do 1, bring the x down to the bottom, or you can write it like this. There's the derivative. And that's how we wrote it in. Do you see? Here's our function, square root of x. Our derivative is 1/2 with the square root of x on the bottom, just like we wrote. And there's a dx. And the dx is 0.5. We already wrote that up here. The dx and the change of x are the same thing. Dx is 0.5. So we just plug them into the formula. Here's the formula. Once again, this is the formula. Here's the function. So we change everything to here. And we have the square root of x. Let me raise that up a little bit. we have the square root of x plus 1 over 2 square root of x times dx. Well, x is 16. By the way, you don't need a calculator for this because Newton didn't need one. He knew how to do fractions. And dx is 0.5, or we could say dx is 1/2 because Newton liked fractions, I'm assuming. So let's do the math here. The square root, so I'm going to first find my pen. My pen disappeared on me. There it is. I'm going to erase this stuff on the right. So we have, I'm still going to erase this stuff on the right.
That's square root of x isn't 16?
Yes, square root of 16 plus 1 over 2 square root of 16, by the way, times 1/2. Yes, there's 16 goes everywhere there's an x. Square root of 16 is 4. 1 divided by 2 times 4 is 1 over 8 times 1 over 16, or 1 over 2. This becomes 4 plus 1 over 16. So the answer is 4 and 1/16. But if you 1/16, if you divide 1 by 16 using long division, because Newton didn't have a calculator, obviously I'm using long division. 1 divided by 16 on your calculator ends up being 4 plus 0.0625, which is 4.0625. This is how Newton did it. This is an approximation for the square root of 16.5. The actual answer for the square root of 16.5 is very close. 4.062, and then just he wasn't too far off. He got it to 3 decimal places using this method. So once again, differentials is to approximate the square root of a number.
Quick question, Mr. Troutman. For us to reach the result that you had circled last, the 4.0625,
Yes.
are we supposed to completely, like, so for us to get the value from 4/116 to 4.0625, should we avoid using a calculator, or what would...
Newton did, however, this test you're allowed to use a calculator.
Or
I
is
mean,
or is
you
4/116th, would that be the exact
No,
answer?
I want the decimal, because it's going to be multiple choice and the answer will be in decimal form. Okay? And what people often do on this, by the way, what the error that people often do, and by the way, it happens a lot. People see the square root of 16.5 and they put it in their calculator and they put 4.0620 because the answers are in 4, it says round to 4 decimal places. And they put this down and it's going to be marked wrong because the correct answer using differentials, it's going to say find the square root of 16.5 using differentials. The correct answer is this, because it's differentials is the approximation, and we want to get the answer Newton got, not by typing it in our calculator. So yes, you can do 1 divided by 16, or you can just put it in your calculator, and like I did to get this. Calculators are okay on this test, but if you type in the square root of 16.5, I promise you will get the answer wrong, because you're going to type in 4.0620 when the answer is 4.0625 using differentials. Okay, so be careful about the calculator. In this problem, they don't want the exact answer. They want the approximation. Using differentials, give you the approximation. So many people in my classes in the past just said, screw it, I don't want to go through all this. And just type in square root of 16.5 and they type that answer in. I think it wasn't multiple choice. I think I said type in your answer to 4 decimal places. You know, I don't require work for this test for the rest of the semester. I'm not going to require work. I really should, but I'm not going to require work. But you got to answer the question. Find the approximation using differentials. You can't just type in square root of 16.5 in your calculator. It will be wrong. I hope that answered that.
It did. Thank you.
Okay. So let's see what else is. Was this the last slide? Because I want to do another, at least one more. Yeah, that was the last slide. So I'm going to go to my whiteboard now, and I'm going to do another one. I'm looking in the homework, and it might, and I'm looking in the homework in the back, in the book, in the back of this section, and I want to find. Let me see where they are. I know I had some more examples that I wanted to do. If not, oh, there they are. Here's one. This is let's do this one. Let's see if we can do this one. This is going to be a little bit different. It's going to combine two things for me. The third root of 26. So we're not even doing a square root this time. We're doing the third root. Here is my function. Okay, so don't forget, here's what I want. Function x plus change of x equals the function of x plus the derivative of the function, then dx. Okay, so somebody tell me what, there's a couple of things I need. I need to know what x equals. I need to know what the change of x equals. I also need to know, I think that's it, the x and the change of x for now. Can somebody tell me what x equals?
Is x the cube root of 26?
No. Remember, if you look at the previous problem, the first thing I did, I'm not going to go back to the previous problem. If you look at the previous problem, the first thing I did was find, what was the previous problem? The previous problem was the square root. The previous problem was the square root of what?
Was the square root of x?
16.5, right?
0.5.
So I had to find a perfect square, and 16 was the perfect square. So x equaled 16, and the change of x equaled 0.5. Right? This has to.
Understood.
These two have to add up to whatever's in here. You see, these two add up to what's in the radical. So I mean, this really takes a little thinking. What do I want to use for x? What's the perfect third root that's close to 26? Okay, I'll tell you then. How about 27? The third root of 27 is 3. 3 times 3 is 9 times 3 is 27. So my x is going to be 3. Do you see? The third root of 3 is 27. But now I need to find a change of x, because oh, by the way, I said 3, but it's actually 27, right? Let me look. My x is going to be, x is going to be 27. And I already said x and change of x have to add up to 26. So my change of x has to be a -1. Right? The third root of 27. The third root of 27 does equal a whole number. I need to find a perfect third root. And 27 is the closest number that get to 26 that's a perfect root. The only way for me to get to 26 is by subtracting 1. My change of x is going to be -1. So my x is 27, and my change of x is -1. So I put them over here. Let me erase these. Get out of here. So I need to find my derivative. Now here's my function. My function is going to be the third root of x. My function is going to be the third root of x, the third root of 27, third root of x. If I have the function that's the third root of x, what is the derivative? Another way of writing the third root of x is x to the 1/3. And the derivative of this, bring the 1/3 in front and subtract 1. 1/3 minus 1 is a -2/3. Another way of writing this is 1/3 to the third root of x squared. That makes a little messy there. Does everybody see? The 3 comes down here. This is the root. It goes to the bottom now. It's positive, but the top is the power of the x. Would everybody agree that this is my derivative? I just want to make sure everybody understands that's the derivative.
Yes.
Okay. So it's important to be able to take the derivative of this. So my derivative is going to be 1/3 third root of x squared, and then dx, or the change of x. Okay, so let's plug everything in here. X is 27. 1/3 third root of 27 squared. Do you see? X is 27. X is 27. And the change of x is going to be -1. The change of x is -1. So the third root of 27 is 3. So here I'm left with 1/3. Now, when you have, by the way, this is algebra. When you have the third root of 27 squared, it's the same thing as saying the third root of 27 squared. They both mean the same thing. That's from algebra. So I'm going to take the third root of 27 first, and that's 3. And then I square it. 3 squared is 9. Oh, by the way, times -1, that just changes this to a minus. That times -1 changes that plus sign to a minus. So we end up with 3 minus 1/27. And let's find the decimal equivalent to that. I mean, you can go through the whole process, but I'm going to use my calculator. And I get to 4 decimal places, 2.96296. So if I go to 4 decimal places, I get 2.9630. And once again, that's my approximation. And if you put this into your calculator, the actual answer on my calculator is 2.96249. If I go 4 decimal places, 2.9625. This is the actual answer to 4 decimal places, 9625. and the actual answer 9630. This is the approximation. So once again, don't type this into your calculator and say this is the answer. It will be wrong. I want Newton's approximation for it. It's going to say use differentials to find the approximation for the square root, the third root of 26. All right, so try a few of those, you know, try a couple of different ones. In the book, I'm looking in the book on page, it's hard to find. On page 277, there's question 47, 48, 49, and 50. I wouldn't even worry about 50. Don't do 50. I don't want to do third powers. But you could do something similar to that. I don't want to do number 50. But, I mean, hopefully there's some. I don't know if there's any of these in the homework. I'm hoping there's some of these in the homework. If not, try a few. You know, try these two over again. And I have time. I want to do, let's do one more. Let's do the square root. Let's do the square root of 8.7. So once again, let me start off with our standard formula, x plus change of x. And then we have f of x plus the derivative plus dx. So there's only two things I need to find, x and change of x. Once I have x and change of x, and then I have to find the derivative, and I have to find the derivative, I'm okay. So can somebody tell me what x equals?
9.
We're doing regular square roots now.
Is it 9?
Yeah, it's not. Square root of 9 equals 3. And so the difference between 9 and 8.7, remember when I add these two up, it has to equal 8.7. So I get a negative 0.3 here. My change of x, 9 minus 0.3 is 8.7. So there we go. Okay, so now I have to plug everything in, but so my function, once again, my function is going to be the square root of a x, the square root of 9. I'm starting off with the square root of 9. I have to find, if my function is the square root of x, another way of writing square root of x is x to the 1/2. To find the derivative of this, you bring the 1/2 in front and subtract 1. Another way of writing this derivative is 1/2 square root of x. So there's my derivative. And if you look, it's the same as the first one of these square root problems we did. The derivative of square root of x is always going to be the same. It gets different when you start doing third roots, because then you have to take the derivative of third root of x is going to be the same also. But the derivative, if we're doing a square root, will always look like this. So the derivative equals 1/2 square root of x. So I'm going to plug this in. The derivative is 1/2 square root of x. And then my dx is going to be a negative 0.3. My dx is my change of x. All right, so I'm going to plug in my x. X is 9. We already stated that. Square root of 9 plus 1/2 square root of 9 times, by the way, Newton would never put a decimal down. Negative 3/10. I don't know if Newton would ever put a decimal down. Normally I don't. Because he has to do the math here. And so then square root of 9 is 3. Square root of 9 here is 3, so 1 divided by 2 times 3 is 1/6. And then we're going to multiply this by negative 3 over 10. This becomes 3 and a minus. The negative and a positive here turn to a negative. The 3 cancels into 2, and I get minus 1 over 20. 3 minus 1 over 20. And when I put that into my calculator, 3 minus 1 divided by 20, or if I did the math by hand like I'm supposed to, I get 2.95. And when I take the square root of 8.7, I get 2.9495. If I take it to 4 decimal places, I get 2.9496. And here it's an even, so it goes to 4 decimal places. If you look, we're pretty close. We're only we're only 10 thousandths off. 94969500. You see, if I added 4 to this spot, I would have the same thing. So we're really close. Square root's really close. The third root seems a little further away, but the square roots were really close for noon. Once again, this is the approximation using differentials for the square root of 8.7. This is the exact answer in our calculator, rounded it to 4 decimal places. This is the one we're looking for. Don't type in the square root of 8.7 and type that as your answer. Some of you will, probably the people not here and the people who don't watch the video. All right, that's all I had for today. Any questions? Watch the optimization video. Those are really important. The video I had on 4.7, we just covered 4.8, and we covered everything we need to for this next test. Thursday, there's no class. I won't be taking roll, but I will be here Thursday. I'll be here to answer any homework questions or any other review or any questions you have. So I'll be online Thursday at least for an hour until everybody leaves. If people stay and keep on asking questions, I'll stay for the whole 2 hours. But if you're here Thursday, just have a quick question, and then nobody shows up within an hour, I'm going to call it a day. All right, you guys have a good day. I'll hang around if there's any other questions. Wait, let me hit stop record.